Okay, so let's do a little bit of theory, and this is perhaps the simplest way to derive expressions for the optimal value of B0 and B1 that minimize the least squares error. Right, so this is for fitting a straight line to data. So given data, like we did last time, xi, yi, I equals 1 to n, and xi, yi in R, set of real numbers. Okay, so the mean square error is given by 1 over n, I equals 1 to n, yi minus b0 plus b1 xi whole square, right? And so we want to minimize this expression. We want to find the value of b0 and b1 that minimizes this quantity where yi and xi are known constants, right? So because that is the data, they are known, and what is unknown are b0 and b1. So let us just expand this out. What we will find is that this is essentially a quadratic function in b0 and b1, and then you take the derivatives, partial derivatives with respect to b0 and b1, set those partial derivatives equal to 0, and solve for b0 and b1. That's the procedure. I'm just going to go over quickly that derivation. The derivation itself is not super important, but it just gives you a sense for, okay, how do you minimize a quantity like this, or at least one of, well, lots of different ways of minimizing some nonlinear quantity. Okay. This is something that you might have done in perhaps your calculus course, potentially, or a statistics course. Okay, let's just expand this. 1 over n, summation 1 to n, yi square plus, well, plus b naught plus b1 xi whole square minus 2i. Okay, so just expanding that out. And then now let's expand this out. B naught square, b1 square xi square plus 2 b naught b1 xi minus this quantity. Oops, I dropped my pen there. Okay, so that's that. Now let's actually simplify things a little bit. Let's take the n to the other side, because n is just a constant. Minimizing the mean square error is the same as minimizing n times the mean square error, because n is just some constant. So let's do that. So n times MSE equals this whole thing. But this whole thing consists of a number of different things. So there's the summation I equals 1 to n. So what I'm going to do is I'm actually going to drop, the I equals 1 to n, because that's understood. All the summations here are over all I. from 1 to n. So I'm just going to go summation yi square. So that's the first term. And then b naught square summation 1 to n, right? So plus b naught square summation I equals 1 to n of 1 essentially, right? So sitting inside the brackets is the number 1. And then plus b1 square summation xi square is what we have here. And then we have plus b naught b1 2xi is what we have here. And then we have these two terms. I'm going to pull the b naught out and then the b1 out. So we're going to have plus b naught. And the coefficient of b naught is minus, oops, I guess I made a mistake here. Okay, similarly, and then b1 minus 2 summation xi yi. Okay, so those are all the terms that we have here. Yi square, b naught square, summation of 1, because when you take this inside, we're essentially summing b naught square n times, and then similarly b1 square times summation xi square, and 2b naught b1 times xi, and so on. Okay, so that's what we have. Okay, so this is some quantity. Now we want to minimize this quantity, and we want to minimize this quantity with respect to b naught and b1. In other words, we want to find the value of b naught and b1 that minimizes this quantity. Okay, so how do we do that? We just set to minimize this quantity, we just set the partial derivatives of this quantity with respect to b naught and b1 equal to 0. With respect to b naught and b1 separately, and set equal to 0. Okay, so let's do that. So what do we have? We have partial with respect to b naught. This quantity with respect to b naught is 0 because that's just a constant. There is no b naught dependence there. So 0 plus this quantity will give you 2 b naught, and then summation 1 to n of 1 is just n. So it's going to be 2 b naught n. This quantity has no dependence on b naught, so that's going to be 0. This quantity is b naught times b1 2 summation xi. When you differentiate with respect to b naught, all you're left with is this. And this again, what you're left with is this. And here, this has no dependence on B naught, so that's 0. Okay, so that's equation number 1. And then now let's take the partial derivative with respect to B1. What did we take the partial derivative of here? It's going to be basically n times MSE is what we took the partial derivative with respect to of. So n times MSE is what we have here. So again, let's do the same thing. This has no derivative, 0 derivative with respect to B1, 0 with respect to B1, 2B1 summation xi square. Okay. Here, B naught 2 summation xy. And then here, this of course gives you 0, and this gives you this quantity. Okay, so that's going to be equal to 0 because when we want the optimum of a function, we set the partial derivatives of the function with respect to its various variables to 0 if there are no other constraints. Okay. Okay, so these are two equations. So we can write these two equations in sort of a simpler form. Notice, first of all, that these two equations are linear in B naught and B1. Okay, they're linear in B naught and B1. There's B naught here, there's no B naught squared or B1 cubed or whatever like that. There's just linear. So and then this is a constant because this is, these things are just dependent on the data, which is considered to be known. Okay, so let's write this in matrix form. 1 and 2 are linear in B naught and B1. So we can write this in the following manner. We can pull out the relevant coefficients here, like so. Let's pull out, well, let's actually write this matrix. Say go B naught, B1 equals some right-hand side. The first equation here, the coefficient of B naught is going to be 2n. The coefficient of B1 here is going to be 2 sigma xi. Well, in principle, you can cross out the 2's everywhere. So let's do that, actually. Okay. And then on the right-hand side, we have summation yi. Here we have, again, a whole bunch of 2's, which we can cancel. And the coefficients of B naught is going to be summation xi here. B1 is going to be summation xi square. So the right-hand side is going to be summation xi yi. Okay. So let me box this equation. So this equation, let's call this equation number 3, is sometimes called normal equations. And if you wanted to solve for B naught and B1, of course, it's relatively easy. It's just two equations and two unknowns. Easy to solve for B naught and B1. And if you want to solve it numerically, of course, you can do it in the following manner. But so you can just go and summation xi, summation xi, summation xi square, inverse summation yi. Okay, so that expression this is basically the solution. These are the best possible values for B naught and B1. Okay, so exercise, try this and compare your solution with the solution obtained from FitLM. And you should see that the solutions maybe are different by, let's say, 10 to the minus 14 or 10 to the minus 15, roughly, or maybe even lower.